Hello everyone, I am Vivek Gupta from University of Utah. I am presenting on TansKBLSTM, an external knowledge enhanced transformer based BiLSTM model for tabular reasoning. So let's first introduce the tabular reasoning problem. In tabular reasoning problem, it's very similar to a standard NLI. The only difference is here we are given a table premise rather than a sentence premise, and the task is given another sentence is a hypothesis. We have to determine whether it is true, false, or undetermined. That is entail, contradict, or neutral. You can check our earlier work info tabs for more details. So the main thing which we are looking in this paper is how can we make this task of tabular inference where there is a premise which is a table, and then there is a hypothesis statement which we have to determine whether it's entail, contradict, and neutral work well by adding knowledge to it. So how can we basically add some external knowledge to make this model improve? The data set which we deal with InfoTabs shows that this task actually requires lots of common sense and knowledge to work effectively. So the task which we look is to use external knowledge graph which can supplement our deep learning models to improve reasonings. So in this example, as you see that this is a table about James Hetfield, and James Hetfield was born on the west coast of the USA. Now to answer this, one need to know that California is a coast and it's located in the west side. So this can be found in a knowledge graph, and if we can use this focus relation from the knowledge graph and transfer this effectively in the model architecture of tabular inference, then we can make this model work. So the main motivation behind this work is there are some recent work which shows that using external knowledge specifically for tabular reasoning is beneficial. Most of these work, however, just added the external knowledge has an input context, which doesn't have its own challenges, and which in terms of like is how that extra context will be treated by the architecture differently from the input, which is basically the table and the hypothesis sentence. Primarily, we answered the following three questions. So first question is related to knowledge extraction. So how can we basically, given the table and the hypothesis, how can we know which knowledge to extract from and where to extract from? So this is the part of knowledge extraction. How can we contextually extract contextually relevant knowledge? Second is, okay, we extracted the knowledge. How should we represent that knowledge? Should it just go as an input in the, as an additional input context in the original thing, or can we do something better? Can we use some semantic knowledge representation or knowledge relations representations which can be used for better representation of knowledge? Third is, okay, we now represented the knowledge as well as we are original model. How can we integrate them seamlessly and systematically? So there are some work which point that it's not so easy task, you just putting them embedding together and doing a classification kind of thing. They need to be integrated in different way, and different models work differently. So we also investigated on how we can do knowledge integration in this stuff. So overall, the takeaway of our paper is like through a knowledge architecture which we call TansKBLSTM, which is a mixture of transformer and LSTM, basically BiLSTM, that is incorporating knowledge base KB, to investigate the inherent challenges in existing methodologies for knowledge addition, extraction, and integration. And we check this effectiveness on the tabular NLI InfoTabs dataset. So the challenges, as I told you, is three side, which is external knowledge is there. We want to add it, extract it, and integrate it. So first, let's look at the extraction thing, how we can extract the knowledge. So before going to the exact approach, I want to show some highlight of the previous approach and what the problem with them is. So Nija et al. 2020 NACL paper shows that you can do KG explicit knowledge to actually improve this task of tabular inference. So here what you are seeing, this is the original premise, which is just linearized or converted into sentential form. So this is a table about Julius Caesar, and basically it's converted to sentence. Now what KG explicit do is they add definitions of the keys. For example, the first key is born, second key is died, third is resting place. So it finds the relevant rows which is related to the hypothesis through a fuzzy method of alignments and static embedding fast text, and then they add definition of each of the keys. So what we found first is these definitions are lengthy. They contain a lot of things, like for example, definition of died is defined as a pass from physical phase, losing of this. So this is very bulky and definition. These were taken from the Wikipedia, and so that at times they can be very bulky and include things which are unnecessary. Okay, for example, the interesting definition only the resting plane. The rest of them are not relevant also in this case. Sometimes even the extraction can be have issues with disambiguation, and they try to resolve them using BERT contextual embedding and all. But still, there were examples where the knowledge which we added are actually irrelevant. For example, for the bond, they actually added max bond intro rather than adding the definition of what is bond mean, like it's the birth of something. Our solution basically want to get this of lengthy and noisy and problematic longer definitions, and put more structured definition in the model. So to extract that, what we use is sample knowledge graph. So we take knowledge graph, we focus on the some entities which are mentioned in the table, as well as, for example, in the hypothesis. For example, first what we do is we basically see connections between the premise and the hypothesis tokens in the knowledge graph. So for example, in this, James Hetfield was born on the west coast of the USA. So west coast and California has a connection somewhere in the knowledge graph, as shown in the left side. So we found first connection in the premise tables between the premise table and the hypothesis tokens and bigram, trigram, and then we look for those in the knowledge graph. So, and once we have this sample knowledge graph, we can use this relationship between them to basically better embed it. Like we know California is in west coast, let's say, that information can be incorporated, and that can be used then further in the addition process to make things work. So knowledge addition has own challenges. So earlier model, as I told you, was adding definitions which are noisy, and they introduce lots of more unnecessary tokens, and then they use multi-head attention over it, which further exaggerate the problem. So our solution is very simple. We basically separately embed the knowledge, and first we find knowledge connection in the knowledge graph, as I shown in the last slide, which is basically California at location is a coast. So this is getting from the knowledge graph. We first convert it into a simple sentence, which is easy to convert because we can take this relation and convert them into a simple phrase like California is at location, and then we use powerful sentence transformer to basically embed them. Okay, so we basically, instead of just adding this knowledge as a extra context in the input and then just giving it to the final model, we basically separately embed this knowledge with the sentence transformer to do integrate. Lastly, we also look at knowledge integration part, which is like, okay, we embed the knowledge, it's fine, it's good, but how do we integrate it with the thing? So we found one big issue with BERT and other transformer based thing is they work at tokenization level. So which is not very compatible with the knowledge. For example, the California will be break into California, which is itself lost the meaning of the whole entity California. So which is not compatible with the external knowledge which we want to add. So if we want to still maintain California and coast relation well, we switch our embeddings basically at token level, and token level, it's been seen like if BiLSTM really work well in that thing. And this is shown in the earlier work, also commented by some of those, ki if you have limited amount of knowledge very in structure form, that knowledge can really work well and embed really good with BiLSTM model. You don't need transformer based model in that setting. And these models, even transformer based model, also interfere with the pre-trained knowledge and the knowledge which you are giving to them. So it's better using a BiLSTM model which is not pre-trained on something to embed this knowledge. So this is finally a proposed architecture. It's pretty bulky. We call it TansKBLSTM, but I will go into sub part of this one by one. So first is we do pre-processing, which is obviously retrieve relations between premise table and the hypothesis. We find those relations in the knowledge graph. We convert them into sentence. We use sentence in transformer to get their embeddings. Now once we get this embeddings, we basically try to get relation and attention and embedding metrics, and there we use basically BERT kind of transformer. And this is basically looking at the premise and the hypothesis and trying to see how much interrelated they are. And in parallel, we also look at how much interrelated they are in the context, specifically in the knowledge side, which we have incorporated those words. So then we basically give it to BiLSTM encoders, which is like we give them to BiLSTM encoders and see how they embed it. Then we use various attention head, which basically take premise, hypothesis relation, use multi-head attention, and then concatenate them, and then do a linear classification. The compose is the most important part, where we basically take first premise, hypothesis, do a multi-head attention, use the relation, and also get context aware knowledge from it, and then we compose all of these things together. More details are there in the paper, but this is the brief idea of how we basically compose the knowledge. And lastly, we also need to filter out the knowledge as well as get important terms from it, or the main important part of it. So therefore we employ max and mean pooling to get the thing. And finally we basically apply fully connected layer. But before fully connected, you also look at embedding mixed connection. This is just to for example, if the knowledge is not relevant and somebody wants, like we want to ignore that knowledge, we can use the skip connection to basically ignore this and directly use the transformer model to do the classification rather than going through the whole pipeline. So this is a very effective way of integrating both the embeddings, and it kind of acts as a regularizer kind of thing, which to the complex architecture and really help us. So we did on info task, which contain 3 adversarial tests: alpha 1, alpha 2, alpha 3. Alpha 1 is similar to the train set with similar domain and same kind of hypothesis. Alpha 2 has similar domain, but it's an adversarial test set where the hypothesis sentence are flipped by changing 1 or 2 tokens. So label is flipped to contradiction, contradiction flipped to entail, and vice versa. Alpha 3 has tables from very different domains, so there's a very little key overlap between these tables with the training set tables. So this is a zero shot domain or cross domain settings. So we have lots of models which we experimented. First is when there's no knowledge edited, which is Robota baseline. We use the KG explicit models, which was the Nija et al. Baseline, where the definitions were used and added to the extra context to the premise hypothesis when we were given to the Robota model. We also use a K-trans token, which is basically the kind of ablation kind of thing, where we take wordnet based tokens connection, like and relations like synonym, antonyms, and all those things, and just append that to the input thing and see how does it work. And lastly, our proposed approach, which is TansKBLSTM, which is seamlessly integrate. So we look at various things. So first we look how effective is our approach for both limited and full supervision. We also see if it is beneficial for certain kind of reasoning, like for example common sense and knowledge, or numerical or something else. We also did many ablation studies, which is like how effective is skip connection happening, how effective is the knowledge addition part kind of thing. Is knowledge addition directly using transformer or embedding or giving it as a context helps. We also see if we do joint and independent training, what's the difference between. So BiLSTM is encoding the knowledge and transform is encoding the premise and hypothesis. So is independent training good, or like if we do joint training is beneficial. We also have some experiment on MLIP training and transformer size, but you can look at the paper for more detail on this. So first is supervised thing. We found that our model actually do perform well. So there is a bit typo, let me fix it. Yeah, so we found that our model really performed well. So TansKBLSTM beat all other models. So you can see there's an improvement about roughly around 1 to 2% for the in comparison to KG explicit. We found that okay, this improvement become much more significant when we have basically low resource like 1%, 2%. So this is a log scale. So you can see our model always is on the top, and the gap between the baselines are much more significant in lower training regime. So you can see the gap is much more improvement, and the improvement is much more substantial. Our model always outperform other baseline models. Lastly, we see this model is do beneficial for certain types of reasoning. For example, like it's do very well on KCS. It very well do on multi-row reasoning. It also do very well on lexical reasoning. And we go on 2 of them, like look at examples why it do well. So obviously one expected, like knowledge graph has lots of common sense and factual information about world affairs, and for example kingdom is a monarch and like all those things, or west coast east coast information like in the previous example. So these relations really help models to perform well. So this is expected thing. Multi-row reasoning we found very interesting why it do well on multiple rows. So multi-row reasoning is basically we want to see if the model is able to extract information from multiple rows. For example, some premise like Jeff Bridges started his career at a young child. So here the born thing as well as child as well as active, these 3 keys are important. So we want to see how model can retrieve all of them and use them. So earlier models were failing at that, and we found that our relation somehow is able to interconnect or basically do right extractions of the rows pretty well because of the relations between the premise and hypothesis. So as I told you, the extraction way thing, we basically take premise, tokens and the hypertext token and try to see the connections between them. So this is actually, when we embed the knowledge, these connections are much more better learned, and then they are able to do the evidence extraction pretty well. So this is very interesting, and can we look for future work how knowledge integration can help in better extraction. Lastly, we look at the ablation study. So how important is each of the individual component. So first we look at like what if we do to embedding mix connection, skip connection approach thing, and also how the relations basically help. So to experiment this with how important is the knowledge relation, we actually have random noise added to the embeddings and see how does it perform. And we also check models with when the skip connection is improved, and you can see when we any ablation, the skip connection as well as the KB. Obviously KB, when we decrease, the model substantially decrease performance. When skip connection improve, we also get decrease in performance, especially on adversarial data set alpha 2 and alpha 3, and when we remove both of them, obviously the model performs the worst. So removing skip connection and addition of random noise adversely affect the performance. So this is expected. We also check on independent training, like how if jointly training is better or independent training. So the independent training is basically we first train the transformer model and freeze the BiLSTM model, and then we freeze the embeddings which we learn from the transformer model and then train the BiLSTM model. So we found that this doesn't work as good as if we do things jointly, and especially we found that alpha 2 and alpha 3 we need, and even alpha 1 we get improvement if we joint train rather than training on this. This is somewhat expected, like joint training do always work better. So again I will ask you to go away, take a broader picture on what this thing is. We have proposed a novel architecture which is TansKBLSTM. We show BiLSTM is effective, transformer is effective for normal tasks, BiLSTM is effective for integration knowledge, and we can use knowledge base to do all these things. And we solve challenges in knowledge extraction, addition, and integration, especially related to tabular reasoning. We do extensive experiment on InfoTab dataset, and we show that our performance enhanced inference as well as do much better reasoning ability than earlier. So I encourage you to attend the poster session as well as my talk to ask much more question about this thing. Thanks a lot. See you at the course.